So this lecture is supposed to be on the atmosphere and the hydrosphere, but I first need to finish the part that Bill prevented me from finishing last time. And I thought I would start off again with this particular slide because, as I was listening to Michael's talk yesterday and Quentin's talk today about how diffusion is really inefficient, that's true, except if it's a rare gas. And since some of the information might have diffused through your brain, I thought I would just start again with what are primordial isotopes and what are radiogenic isotopes. So again, remember, these are isotopes that are not produced on the Earth. Helium-3, neon-22, argon-36, xenon-130. Radiogenic noble gases are produced from radioactive decay of uranium, thorium, potassium. So that's helium-4, argon-40, xenon-136, and so on. And again, we'll be reporting things with radiogenic to primordial ratios. I showed you last time that the helium-neon ratio was different between the plumes and the morbs. Helium-argon ratios were different between plumes and morbs, strongly suggesting that the plumes cannot be supplying these primordial gases to the morb reservoir, and that these two reservoirs were likely never completely homogenized. I gave you some arguments as to why we think that the helium-neon ratio, these very high ratios in the morbs, are probably a reflection of a magma ocean signal, because the sun and the chondrites are way down here. It's easy to decrease the helium-neon ratio. It's very hard to increase these ratios. So we'll jump through a couple of elements, argon and krypton, and come to one of the most interesting of these noble gases, and that's xenon.
I was thinking about the helium-neon ratio for more, I think, a signal to magma ocean. What about the heavier noble gases? Are those also going to have the same pattern?
So they could have the same pattern, but I'll come back to that. The reason why we think they may not be recording that pattern is because the pattern might have been reset through recycling of atmospheric gases. Helium and neon are not recycled to significant quantities, and I'll show you evidence for that. So again, remember, these are going to be radiogenic to primordial ratios. The important point here is iodine-129 has a short half-life, 15.5 million years roughly, means 100 million years the system is extinct. Xenon-136 comes from plutonium-244, half-life of 80 million years, means after 500 million years the system is extinct. Xenon-136 is also produced from spontaneous fission of uranium-238, which means that the production of this isotope happens all through Earth's history. The production rates were much higher earlier on because the yields from plutonium are significantly higher than for uranium. Just to orient yourself, so this is the xenon-129-130. So remember, on this axis you can move in this direction for the first 100 million years. On this axis you can move a lot in the first 500 million years, and then a little bit after that. Of course, you can again keep moving significantly up in this direction if you have a very degas source. And here are the observations. So the atmospheric composition lies there. This sort of represents the highest measured values that we have seen in mantle plumes, such as like Iceland. And this represents some of the highest measured values that we have seen in mid-ocean ridge basalt. And here I'm plotting the composition of this very gas-rich rock called popping rock from the North Atlantic. So the question is, are these highest measured values what the mantle source has, or are these values representative of some sort of an atmospheric contamination process? So for example, you could imagine that you could produce this composition by mixing this source with atmosphere, and this could have happened either in the source or it could have happened when these lavas erupt. So for example, if these basalts are more contaminated, and I showed you pictures of the fact that most OIBs erupt under subaerial conditions or under shallow water, so it's likely that they might have suffered more atmospheric contamination. And the final possibility is that these morbs and OIBs evolved with different iodine-xenon ratios, and that's really important because, again, that means that these differences might have been set up very early on in Earth's history.
Are you concerned that your OIB is in a morb setting? Iceland is on a spreading ridge?
Iceland is on a spreading ridge. I'm not. So in terms of determining what the pure primordial composition is, it would be a concern. It wouldn't be a concern in terms of showing that there is a difference between mid-ocean ridge basalt and this plume-influenced basalt.
But maybe only plotting where air is and all you're seeing the mixing between more and volume.
We can talk about that, and that's specifically what I'm going to be focusing on. Okay, so a few years ago, Holland and Ballantyne made some really nice measurements from these continental well gases. So these are from New Mexico, associated with the Rio Grande Rift. So this is basically where you'll see most of the mid-ocean ridge basalts plotting. And again, it means that the mantle composition is somewhere up here. Upon eruption, you contaminate the basalt with air, and that's why the individual samples or the individual crushes of the samples will plot on this line. The continental well gases are different. So these are crustal gases, and they have crustal contamination. So if you look at the crust actually lies somewhere way off here because there is no iodine being produced or iodine produced 129 in the crust today. That system is extinct. There's a lot of uranium in the crust, and that produces 136. So that's why the crust is way off there. And these are these well gases from the Bravo Dome, again from New Mexico. And the argument is that it's a mixture of air and crust that then subsequently mixes with mantle. And so where you have the intersection of these two lines defines the composition of the mantle. And that means that the mantle composition is fixed at about 7.9. Okay, so this is very close to what the maximum measured value in popping rock is. So what about for ocean island basalts? And this is what we see for the Iceland plume. So air again lies there. Again, remember, this is one single sample, multiple crushes of the same sample to generate this kind of a mixing hyperbola where you're looking at the shallow level contamination process. So the mantle lies somewhere up here. Upon eruption, again, different population of bubbles get different amounts of atmospheric xenon added to it, and that produces this hyperbola. And this constrains basically the Iceland source to about 6.9. Okay, so it's definitely different from this Morb value of 7.9 plus or minus 1.
So that error bar is the precision with which you know that hyperbola?
That's right. That's right. So the lower values are not related to shallow level contamination process. So it's either related to the subduction of air or air saturated seawater into the Morb source, or it's related to the difference between iodine xenon and plutonium xenon ratios between the plume source and the Morb source. So how do we distinguish that? And here is the plot. So what you're looking at is xenon 129 to 130. So again, remember, no production of this isotope. Iodine produces this isotope for the first 100 million years. This is primordial helium-3, primordial xenon 130. Again, no production of this isotope. The atmosphere lies up here. This is the Morb composition in 129, 130, and this is the Iceland composition in about 6.9. And basically, you see two different trends. And again, these are two samples. This data is from Morera et al. 1998, and this is the Iceland data. And what you see, based on these two different mixing trends, are two different sources. So for example, assume that the whole mantle had the same iodine to xenon ratio. So that system became extinct 100 million years. So you could produce variation in this y-axis through recycling air. But if this is the Morb composition and you recycle air, then you're forced to move down this line. Okay? You cannot get off this line after 100 million years because there is no production of this isotope. So it's impossible to go from here down in this direction if you only have one xenon reservoir in the mantle to which you're adding recycled atmospheric xenon. So these two distinct trends require the presence of two distinct xenon reservoirs in the mantle. And again, that means that you must have set these two reservoirs up within the first 100 million years. Okay, so you can again move up this direction for the first 100 million years, but not subsequently, Colin.
Do you think the mantle, or let's say the atmosphere 129, 130 xenon ratio has been constant with time?
This ratio, has this been constant through time? So it may or may well, let's see. As far as we know, until 3.5 billion years ago, it was constant. And again, there is no reason to believe why this ratio would change drastically in air. Because
Xenon 130, is that the one that comes from the uranium fission?
no, this is only iodine. This is only based on the iodine xenon system. So this is only evolution for the first 100 million years.
How do you know the atmospheric composition 3 billion years ago?
So these are measurements in cherts, where we think we see trapped seawater, and it's measurements of the xenon isotope composition of the seawater. So it's presumably seeing the atmospheric signal.
So just to take a few steps back, the air is different from the mantle because xenon degassed early and more when iodine was still alive.
Hold that thought. So we don't know why they're different. So the point of this figure is that the atmosphere and the mantle are different, and within the mantle there are two different reservoirs that you cannot relate simply through adding air. Maxime.
What about the size of these heterogeneities? Is there a lower upbound of this by you said that the diffusion length is different or higher for this?
It's going to be fairly, well, higher for helium, but probably not that high for xenon. So sort of to give you a rough estimate, helium might be diffusing to length scales of about maybe 50 kilometers over the age of the Earth. Xenon diffusion rates are going to be obviously much lower, although we do not have good data.
Where does the seawater xenon isotope ratio?
So right there. So air and seawater have the same isotope ratios.
Wouldn't iodine be higher than seawater?
It doesn't matter for the present day because there is iodine 127, but there is no iodine 129 anymore. It's an extinct nuclide. Matt.
Sujoy, if I remember right, the isolate sample, the helium-3-4 ratio isn't terribly high.
It isn't.
I can imagine and we talked about this, I can imagine a scenario where the isolate sample actually reflects a mixture between something more extreme, lower 129, 130.
It could be down here.
And 4 reservoir.
It could be down there, but that doesn't erase the fact that these two are very different. But also,
How low it would be? Is there,
no, it's not there isn't an easy way to do that because the Iceland sample does have amongst the most unradiogenic neon isotope signal. So there isn't a very easy way of predicting that. But yes, it could be lower down because you might potentially be seeing some influence of mid-ocean ridge source because it's erupted at a ridge. Dave?
The big variation in either of those is represent mixing with air.
So this is recent mixing upon eruption. That's right. So these are, again, the same measurement or different measurements of the same rock.
Okay.
Yeah.
So can you say something about the highest ratio being more representative about the reservoir?
Yeah, so this is where we think that the reservoir is today. Yeah.
Could there be more than 2 reservoirs? These are only 2 samples.
Yeah, there could be more than 2 reservoirs, but then remember, if you have more than 2 reservoirs, you have to keep them separate. So here's the other important part. Let's assume you produce these 2 reservoirs within the first 100 million years, which you have to do to get this difference. If you subsequently homogenize the 2 reservoirs, this difference wouldn't exist in the present day mantle. So that's a key point. So if you now say there are 5 separate reservoirs, you created 5 different reservoirs in the first 100 million years, and you have not homogenized them all. So that's the implication.
So we think we made DMM continuously over several million years, maybe back to the beginning. So this suggests that DMM was formed in a one-off event in the first 100 million years, or how do you explain
No.
early formation of DMM?
No.
Explain DMM.
So DMM is the depleted Moore mantle. So what this says is that the degassing rate of the Moore source that we see today was different from the degassing rate of the plume source right from the get-go. Rick?
Sujoy, way out of this time constraint, the same thing you can use for hafnium tungsten is that you could bring in this high 129, 130 material well after 4.45 as a meteorite component as a late veneer, for example.
Sure, and I want to address that as well. So I'm arguing, so Rick's question was, you're seeing these two reservoirs. It doesn't mean that it had to have formed within the first 100 million years. Maybe the late veneer brought this stuff in and you mixed it into the shallow or upper mantle. So that's a different interpretation than mine, which was to say you produced this within Earth in the first 100 million years and it was never homogenized. Now, even if Rick is correct, it still requires that the late veneer stuff wasn't completely homogenized throughout the whole mantle, because again, we still see this difference in the mantle today. That's going to be the second part of the talk, which I was supposed to have started by now. But so very quickly to sort of show you that we see the same difference when you start looking at isotope space. So here is the 129, and now that's being normalized to the radioactive isotope of xenon-136. So here's a quiz for you guys. There are 9 isotopes. How many different 3-isotope plot can I make?
The same denominator.
84 of them. So you can make 84 of these 3-isotope plots for the xenon system. So thankfully, I'm only going to show one. This is the iodine-produced xenon. This is the plutonium-uranium-produced xenon. This is primordial xenon. This is the radiogenic xenon-136. So air is here. This is the Iceland source. This is some recent measurements, again, we made from the northern Lau Basin, where you have very high helium isotope ratios reaching up to 28 times the atmospheric value. Here are measurements from the depleted the equatorial Atlantic, very depleted morbs. These are measurements of Southwest Indian Ridge morbs. And the point is, let's assume you have this depleted morb source, you add air to that, you will be again forced to lie on this linear mixing line, because again, mixing in this space is linear, normalizing to the same isotope. If you add air to this Iceland source, you would move down there. So adding air doesn't get you from here down to there. Now, magmatic degassing can get you there, and the reason is the following. If you degas the mantle, you would lose 129, you would lose 136, you would lose 130, and you would lose 136 again. So if you do this after 100 million years, the only thing that you can then produce in the mantle is 136. So for example, the production rate would be somewhere way off here at 0, 0. Okay, right, because you're not producing this, you're producing 136. You're not producing this, you're producing 136. Okay, so if you degas the source and add either plutonium or uranium produce 136, you would end up moving down in this direction. Okay, so as the further down you go in this direction, the more degassed the source has to be, because you have lost this isotope and you have lost this isotope, but you're producing this isotope. So that's why you can move down this direction. So again, what this is telling you is that the source of the mid-ocean rich basalts are more degassed than the source of the Iceland or this northern Lau Basin plume source. So the implication of this again is that you had 2 distinct sources, at least 2 distinct sources in the mantle within the first 100 million years, and they were never completely homogenized. Okay. So if you say that the plumes are coming from things like LLSVPs, which we have talked a lot about, and I'm not saying they are indeed, but if it's coming from LLSVPs, then the implication of this is going to be that material in LLSVPs are at least as old as 4.45 billion years, meaning that these features must have existed, maybe not in its present configuration, but these features at the bottom of the mantle basically must have existed throughout Earth's history, and that they cannot be composed purely of recycled slabs. It doesn't mean that there isn't some amount of recycled material in them, but they cannot be solely comprised of recycled slabs. There has to be some material, or a large fraction of the material, that predates 4.45 billion years in these provinces today. So you can make some very quick back of the envelope calculations. So we know the plume flux is about 1 times 10 to the 14 kilograms per year. If you add in large igneous provinces, you might be able to double this. If you look at the helium isotope ratios in the mantle, the average helium isotope ratio in plumes is about a factor of 2 higher than the average helium isotope ratio in morbs. The highest values are a factor of 6. So the fact that the average is about a factor of 2 higher would indicate that plumes, on average, would have something between 10 to 20% of this primordial material. So if the plume flux is basically being constant over time, and you're entraining about 10 to 20% of this primordial material, then roughly, if you dial the clock back 4.5 billion years, these LLSVPs could have constituted 3 to 7% of the mantle mass. This calculation assumes that the present-day volume of LLSVP are only about 2 to 3%. As Barbara mentioned yesterday, it's possible that these might be about 7% or 8% in the present-day mantle, and so you would add this number to about 8%. So somewhere on the order of maybe 10 to 15% at most is quite compatible with what we think that the rare gases tell us.
Yeah, a comment and a related question. So in this blood Iceland is off of the LLSVP, and the
That's,
question would be,
yeah.
how do these xenon or any other noble gas characteristics compare between different hotspots?
That's a great question. As I can tell you that we have measurements from northern Laos, which is possibly sampling the Samoan plume. We have this one measurement from Iceland. We are planning to make more measurements from Hawaii. But I think if you look at the LLSVPs, they actually will, or Iceland will lie on the edge of the LLSVPs. So this is something that Adam showed in his presentation as well. Matt and Curtis.
Just a comment on that. If you think about the entrainment process that might be occurring, you may predict that you shouldn't see these types of ratios in all oceanic solvents. It may just be a fraction of them or...
That's right. So not all, as I said, not all ocean island basalts come up with 50 times the atmospheric ratio. Some ocean islands actually come up with helium isotope ratios that are more radiogenic than the mid-ocean rich basalts, which we think have high concentrations of recycled crust, for example. Ed.
And not to add another degree of freedom, but if the ultra-low velocity zones are partial melt of something that's not your LSVP,
Mm-hmm.
or even part of them, and they could be hanging out on the bottom, and these things could hide in there and not be actively entrained.
So that means that you would be diffusing the gases from these ultra-low velocity zones into the LLSVPs. Remember I showed you this figure last time where we saw this very nice correlation between lead isotopes and the helium-neon ratios. Short diffusion timescales, I guess. But there's a correlation between lead isotope ratios and helium-neon ratios, or lead isotope ratios and neon isotope ratios. So explaining it through diffusion is going to be hard. You need to...
Well, I don't think that's the only way that you can get this stuff out, because I guess dynamically and morphologically, the ultra-low velocity zones, if they're a tiny bit of partial melt, they're not super low viscosity, so they would act like mini piles. So they also can have their material entrained inside the pile, and then you take
Sure.
a special event for them, that stuff could be entrained while pile material would be entrained.
Sure. So that still means...
Feel to that being too special.
So there are 2 points. One is it still is being entrained, and it is still being sampled today.
Yes.
So this is not... So whatever the rare gas, primitive rare gas signal that we are seeing today is, you cannot appeal to that for the hidden reservoir that Rick wants, for example, because we are sampling this very old reservoir in the mantle today. So it could be LLSVPs, or as you said, it might be ULVZs. The problem is the smaller you keep making the reservoir, the more concentrated the gas concentrations have to be, the more you have to shove things like uranium, thorium, potassium into them. So that's the trade-off.
I'm wondering if you can relate this to the Ross model for the formation of two distinct, one shallow and one deep magma oceans. So one would end up holding, this could be the surviving remnant of the deep magma ocean, holding one xenon
that could be possible. But again, it means that you have two different outgassing rates from very early on in Earth's history. It's very hard to get away from that argument. Mark?
I was just going to say, we may like the LLSVPs because they're the part of the mantle that may have interacted least with the rest of the mantle. But there's a part of the interior of the Earth that's probably interacted even less, and that's the core.
And again, that means to get that signal out. So we don't seem to see that signal in PGEs, but maybe it's diffusing out. Sure, but that means you're diffusing it out of the...
No, it's just vesiculating it.
Without the experimental data, I would not want to go there yet. But, yeah.
If you want to correlate this, if you want to see the LSVPs or the 142 neodymium reservoir,
Uh-huh.
the elementary one, turns out that system's not particularly sensitive to the amount of material that can come back. If you look at the secular change of 142 in the Earth, you haven't seen any since 2.5
That's right.
billion years or so. You could tolerate. Now it was like something like 10% of the reservoir could have come back into the mantle, and you wouldn't know.
You wouldn't know about it. Yeah. Yeah. That's right. Okay, so before sort of moving to the atmosphere part of the talk, the point that I wanted to make was that the helium-neon ratio in the mantle, we think, remembers the presence of a magma ocean. The 129 to 130 xenon in the mantle, we think, reflects two different reservoirs, probably separated by 4.45 billion years, and then subsequently, these two reservoirs were never completely homogenized. So again, we can debate whether that's LLSVPs versus ULVZs or some other reservoir. But the implication is if they're coming from LLSVPs, then these are as old as 4.45 billion years. And I think that the moon-forming impact did not completely homogenize the entire mantle, because coupled with these xenon difference, you also see the differences between helium-neon, helium-argon, neon-argon, and so on, that you cannot relate purely through magma ocean degassing processes. Okay, so I wanted to touch now upon whether we think the gases in the atmosphere, or at least the noble gases in the atmosphere, are some remnants of a primary atmosphere. And what I mean by a primary atmosphere is these are atmospheres that would be directly captured from the nebula. So we can't play this game with things like carbon, nitrogen, sulfur, and so on, because those species have been fractionated isotopically because of biological activity. They've been recycled to a great degree. So if you want to pierce into the deepest part of Earth's history, rare gases actually are really important, because you can use these as fingerprints because they are inert. And I told you that we think, at least in the deep mantle, we see the nebular signal. Now, sort of forgot about this slide, but there's a reason, obviously, why the composition of the earliest atmosphere is important. And this goes back to Harold Urey's work in the early 1950s, and the famous Urey-Miller experiments, where they put an electric discharge into a very reducing atmosphere and effectively produced basically all of the amino acids that we see in living organisms today. They produced complex sugars and so on. And so Urey was a proponent of a very strongly reducing atmosphere because he thought that the planet grew cold. So they were put together by aggregating small planetesimals or dust, so the planet was never very hot. And in that case, if you look at meteorites, you would predict that the atmosphere should be very reducing. On the other hand, Ruby argued that the atmosphere formed primarily through magmatic outgassing. If you look at magmatic outgassing today, you primarily have CO2 and water. These are oxidizing or neutral atmospheres. And prebiotic chemistry in these atmospheres are not particularly exciting. So obviously, the reducing atmosphere is much more exciting in terms of chemistry. So here is the evidence, as I pointed out, based both on the neon isotope ratio and the helium-neon ratio, that the deepest mantles seems to remember incorporation of nebular gases. It's very hard to get this kind of a solar signal into the deep mantle in any other way. So at least the deep mantle seems to say, yes, the Earth at some point had nebular gases. And that's not unreasonable, because the dissipation of the nebula happens on timescales of somewhere between 5 and 10 million years. And the deepest part of the mantles was probably accreted by then. or surely would have been accreted by then. So it's very likely that you would have some nebular gases. Capture of nebular gases will happen by the time you get to the size of something like Mars. And as we know, Mars basically grew to its size in about a couple million years. So if you extrapolate that to Earth, this is a very likely scenario. Now, if you look at the atmosphere, that's a very different thing. So this is looking at the atmospheric pattern for helium, argon, krypton, and xenon. So this is basically normalized to the silica content of the Earth and then the silica content in the Sun. So this would be things like neon to silicon in the Earth divided by neon to silicon in the Sun. So by default, the Sun would have this very flat pattern. This is Earth. Chondrites do this, and Mars does something like this. So basically, you can look at this and say, A, the atmosphere is massively depleted in rare gases compared to the Sun. This overall pattern looks nothing like the Sun, because if it was the Sun or nebular gases, you would expect a flat pattern. Instead, this pattern very closely matches what we would call the chondritic pattern. Okay. And here's another example why we think some of the other volatiles could not have come in from the nebula. So if you look at the nitrogen to neon ratio in the Sun, it's about 1. The nitrogen to neon ratio on our planet is something like 86,000. Okay. So massively enriched in nitrogen compared to neon. So that means, A, that most of the nitrogen must have been delivered in some sort of a condensed phase, and it wasn't captured directly in from the nebula. So in terms of this overall pattern, it does not look like a primary nebular atmosphere. So at least the atmosphere does not remember its presence if it was there. We think that the deep mantle remembers it. The atmosphere, or the present-day atmosphere, does not remember it.
Is there anything to be made of the ordering there?
You would, well, yes and no. You would expect also smaller planets to lose more noble gases compared to larger planets. So in that respect, Mars kind of makes sense that Mars is more depleted. Why Venus is less depleted than Earth, I'm not quite sure.
How much would the different solubilities of nitrogen and neon in the magma ocean?
No. No.
It's small.
Yeah, it's small compared to this 86,000, yeah. Okay, so at least the noble gases in the present-day atmosphere is a secondary atmosphere, and you can produce a secondary atmosphere through 3 different ways. Either through impact degassing. This could be happening while you're accreting and building the planet up. It could happen later on, associated with something like a late veneer. You could be outgassing the Earth's mantle, and then I already mentioned late veneer here. Okay, so as I told you that the atmospheric noble gases have an elemental abundance that looks very similar to what we see in carbonaceous chondrite. So can we explain the atmospheric gases through accreting chondritic material? So here is a figure from Marty's EPSL Frontiers paper. So this is deuterium to hydrogen ratio to nitrogen 15 to nitrogen 14 ratio. So this is the Sun, based upon measurements from Jupiter. Earth lies here. These are long period comets. This is a Jupiter family short period comet. And a lot of the chondritic meteorites lie right there. So the take-home point from this initially was that if you had long period comets, they can't deliver all of the water to Earth because their deuterium to hydrogen ratio is on average a factor of 2 higher, right? So 1.5, somewhere around 3 to 4 times 10 to the minus 4. So it might have contributed a small portion of the Earth's water, but not all of the Earth's water. On the other hand, the short period of the Jupiter family comet basically have the right deuterium to hydrogen ratio to deliver Earth's water, but not in terms of the nitrogen isotopic composition. So the short period comets are good in terms of matching the water composition, not in terms of matching the nitrogen composition. There might be a way out of this because the nitrogen measurements are based on HCN. So that's basically the organic component. If there is N2 dissolved in water, we don't know what, dissolved in the ice, we don't know what its isotopic composition is in Hartley 2. What do comets look like 3 billion years ago? I don't know. Does anybody? Bill knows it. So there's another point that I do want to make, which is if you actually look at Earth, and if you look at the Sun and these long period comets, they do sort of align on a kind of mixing line. Right? Now, one of the things a group here could do is, if I'm making the claim that to get the solar neon into the Earth's mantle, you need to dissolve nebular gases, then you know at the same time you have to be getting a lot of hydrogen because the nebula is 96% hydrogen. And that hydrogen will have this isotopic composition and this nitrogen isotope composition. So it is possible that comets might actually be contributing, even these long period comets, if they're representative of other long period comets, they might contribute more than the canonical 10% that's thrown out in the literature. Jackie?
So the nebula gas and the solar, they are the same with certain isotopic composition, but different with water. So for nitrogen, you are equaling like these two.
Well, we think that solar and nebular gas will have the same isotopic composition.
For everything. But I thought earlier you actually emphasized that the sun, like the different nebula.
No, the sun and the nebular gas would be the same. Do you remember which?
I think she's referring to photos.
These?
Actually, some of the ratios in Jupiter and the Sun are different. How do you explain those relative to what the solar nebula composition would have been? Well, I thought they had different, like, helium isotope values.
There are different helium isotope values than the present-day Sun, but we understand that through something like deuterium burning. So we do. I mean, the Sun is basically 99% of the solar system, so it's hard to make the nebular gas be very different from the Sun's composition, Bill.
At some level, I was asking that question facetiously because one might expect comets to have started out with nebular gas composition. Not required, but possible.
Possible.
Logical, too.
Okay, so you could get the hydrogen and the nitrogen either through some sort of a mixing, or if you look at the chondritic meteorites, they have roughly the right composition, both in terms of the deuterium-hydrogen ratios or nitrogen isotope ratios. So the preference for getting the water and nitrogen and carbon is to call upon delivery of things that look like carbonaceous chondrites.
The flux of solar neutrinos was associated with deuterium. So the objects closer to the sun would have a higher flux of solar neutrinos. Is that taken into consideration?
I don't know, and I'm not sure how important that would be. Okay, so we've seen this picture before showing you exactly what the Earth looked like as it was being hit by something the size of Mars. So associated with this moon-forming impact, we think that a large part of the mantle must have been devolatilized, and most of the volatiles must have been transferred to near surface reservoir, either in the atmosphere, which was at that point a silicate vapor atmosphere, or close to the surface. Mark has a paper out in EPSL that talks about the consequences of magma ocean degassing, and he shows that the carbon, oxygen, hydrogen species are going to be very strongly controlled by the magma ocean fugacity, and there's potential for having zonation in the magma ocean associated with the iron disproportionation. But it's likely that the upper part of the magma ocean is going to be sufficiently oxidizing that the atmospheric species, after the atmosphere cooled, would be dominated by H2O CO2. So again, something that would be neutral to maybe slightly oxidizing. So if most of the volatiles came into the Earth prior to the moon-forming impact or associated with the moon-forming impact, one would argue that the atmosphere that formed after that would be dominated by H2O CO2. So this could obviously be a steam atmosphere. Colin?
Is that conclusion with the early Earth atmosphere being relatively oxidized? is that dependent on the radius of the planet? Like if it were Mars-sized or an accretion of the early level gases, would the atmosphere also be more reducing?
So this is, I believe, the last impact, the last moon-forming giant impact, and Mark can say a little more.
Speculation, it's not a,
Yeah.
but second of all, yes, it very much depends on the pressure of the magnet. So therefore, the size.
Yeah. What I'm going to show you is that I think it's actually possible, at least, that you might end up with a reducing atmosphere, especially if a large fraction of the volatiles are coming in after the moon-forming impact. And I'm going to show you with the rare gases why I think that the atmospheric rare gases, A, cannot be derived by mantle outgassing, and B, have to come in after this moon-forming impact. And so if you're bringing in a large fraction of the rare gases in the atmosphere after the moon-forming impact, you also have to bring in all of the other volatiles, water, carbon, nitrogen, and so on. You just can't decouple those two. And so here is the first figure. So this is showing you krypton isotopes, 6 isotopes. And the isotopic composition is normalized to krypton 84 and to the amount of krypton 84 in the air. And by default, the atmospheric pattern is going to be flat. Okay, so that's where our atmosphere lies. This is the composition of the sun based on solar wind measurements. And in black squares are a bunch of measurements of carbonaceous chondrites. Okay. So basically what you see is that the Earth's atmosphere is depleted in lighter isotopes, lighter krypton isotopes compared to the sun. It is also enriched in the lighter krypton isotopes compared to chondritic meteorites. So remember that even though the pattern, the elemental abundance pattern in the atmosphere looked very much like carbonaceous chondrite, you simply just cannot bring in the carbonaceous chondrite because it won't give you the right krypton isotopic composition. This is now the 9 xenon isotopes in all its glory. And things are normalized to xenon 130. And again, the atmosphere is right there. It's got the flat pattern. And now you notice that both the sun and chondritic meteorites are enriched in the lighter isotopes. Or the other way to say it is that the Earth's atmosphere is depleted in lighter isotopes compared to both the sun and the carbonaceous chondrite. Okay? So that's a strange conclusion because in this space, the atmosphere has more of the lighter krypton isotopes compared to a meteorite. In this space, the meteorite has more of the lighter isotope compared to the atmosphere. So it's a very difficult puzzle to solve. Patrick?
What is the figure on the right?
This, I believe, is Pepin and Percelli's 2002 annual reviews paper. Or, sorry, Reviews of Mineralogy chapter. Sorry, I don't have the citation here. Okay, so mixing and matching of solar and chondritic gases gets you into real trouble in terms of matching the atmospheric pattern. So you could invoke something like a mass fractionation process that affected atmospheric noble gases. And that was being invoked since the 1980s by Hunton and Donahue, and for the noble gases popularized by Pepin, who has a very nice chapter in Icarus in 1991 on the formation of the atmosphere. So moving to a different element, and this is again just in cartoon. So the neon isotopes, so this is the sun, this is the Earth's mantle, atmosphere, carbonaceous chondrites. So basically, again, the atmosphere is depleted in the lighter isotopes or enriched in the heavier isotope compared to the mantle. And there are two ways of doing this. You can either explain the atmospheres through some combination of mixing chondritic gases with outgassed mantle gases. That's possible. That mixture puts you somewhere down here. Or you could outgas the mantle, this composition, and you could lose a large fraction of the neon that you outgas. And the way to do it is if you have a very large hydrogen-rich atmosphere, you can have a hydrodynamic escape associated with a very early energetic sun, where you're dumping a lot of deep UV into the upper atmosphere. You're driving very high rates of hydrogen escape. The hydrogen escape rates are so high that they're dragging things all the way up to xenon, something that is 60 times heavier with it. And this process leads to a mass fractionation whereby you preferentially lose the lighter isotopes and you retain the heavier isotopes. So the atmosphere would get enriched in the heavier isotope and be depleted in the lighter isotope. So if you outgas this mantle composition and you have hydrodynamic loss of the atmosphere, you would preferentially lose neon 20 compared to 22, and you would bring the atmospheric composition down. So these are the two possible ways of explaining the neon composition, and that would also work for something like the mantle. If the mantle has this composition, as you progressively lose this gas composition, you would be losing the lighter isotopes. So basically this kind of a pattern that you see would slowly rotate like this as you preferentially lose the lighter isotopes. Okay? So we have to distinguish between these two possibilities in terms of how can we explain the process. And this is shown beautifully here by this recent paper by Bernard Marty. He's plotting the neon isotope ratio against the argon to neon ratio. So the sun's composition lies right there. This is the maximum measured value that I had from Iceland. This is the composition of the depleted mid-ocean ridge basalts. This is where our atmosphere lies. This is where we see a lot of the chondritic meteorite compositions. This is the curve associated with this kind of a hydrodynamic escape process, some kinetic fractionation, where you preferentially are losing the lighter isotopes. So you would evolve along this curve. So if you start off here, if that's your mantle composition, you outgas this mantle composition and start losing the atmosphere, you would evolve down in this direction. And notice the true composition of the atmosphere, it's way off there. On the other hand, notice that it's very nicely explained by this kind of a mixing relationship, where you can explain outgassing, a little bit of outgassed solar neon from the mantle with this more chondritic composition of neon in the mantle. Impacts can certainly remove atmosphere. We think that most impacts lead to bulk ejection of the atmosphere, unless you have things.
So impact would also move you along that line from solar towards the
No, because it would lead to a fractionation in the atmosphere, right? You have to change the neon isotopic ratio. So people have proposed that impacts might lead to isotopic fractionation if you thermally heat the atmosphere. But those calculations haven't been done yet. If you have just a bulk ejection of the atmosphere, then you just decrease the inventory without actually fractionating the isotopes. And in this case, what you see is the atmospheric isotope ratio is different from the mantle isotope ratio. So whatever process you have to invoke, you have to fractionate the isotopes. But yes, it's quite possible that you could generate this through some kind of an impact process. But again, I think that impact process would be on this curve, because that's your.
What study are you referring to specifically suggesting loss of atmosphere?
Oh, this goes back to Jay Malosh's work and Tom Aarons's work in terms of bulk ejection.
Showed that
Yeah.
in fact they had they proceeded in fallacious fashion. They hadn't looked at these, used the scale height of the atmosphere. When you actually put in the decrease in pressure, in fact, you lost very little.
So the best work on this, I think, goes back to Genda and Abbey, who showed that how much atmosphere you lose critically depends on whether you have liquid water on the surface or not. Right. So if you have rock at the surface, then you can lose a lot of the atmosphere. The moment you put a little bit of water, you lose a lot less because the impedance.
The other way around.
Is it the other way around? Okay, yeah. Sorry. Yeah, these are measurements in carbonaceous chondrites. Yeah, let's not even go there. So you can see neon has two isotopes. If you look in the meteoritic literature, people have identified 7 or 8 components. There's like neon A1, neon A2, neon EL, neon EH. That's 4. Neon Q. So let's just not go there. Okay, but I'll come back again to Michael's question about whether you can relate this to some kind of an impact process. So we've known for a long time, or at least since the end of the 1990s, that the mantle 128 to 130, so these are primordial isotopes, the mantle is different from air. So here what you're looking at is the atmospheric composition here. This isotope ratio doesn't change in the mantle. This is 129 to 130. This ratio does change in the mantle only for the first 100 million years. The atmosphere is down here. The sun's composition or meteorite compositions plot way up there. Okay, so the mantle samples, so these are well gas samples from New Mexico, plot up here. These are measurements from mid-ocean ridge basalts. This is the measurements from mantle plumes. They plot along this line, and you cannot relate the atmosphere to these compositions directly through any kind of mass fractionation process. The mass fractionation process goes like that. So one possible explanation for these measurements is that the atmosphere or the mantle originally was way up here. You in-grew 129 from iodine decay and moved out in this direction. Then you started subducting atmospheric noble gases into the mantle, and that pulled the composition back down. Maybe if you wait another couple billion years, all of these mantle sources would evolve back to the atmospheric composition. Okay, but the bottom line is that the atmospheric 128-130 is different from the mantle 128-130, both for the plume source and for the MORP source, so basically the entire accessible mantle. And then a couple years ago, Chris Ballantyne's group produced this very interesting measurement. So if I again go back here just 1 second, just to point out that in this case, in terms of this primordial isotope ratio, notice that the mantle, again, is enriched in the lighter isotope compared to the atmospheric gases. So again, if you have very early degassing of the mantle, before a lot of this iodine would have decayed to xenon 129, you might have been up there. As you lose that atmospheric xenon, you could have potentially moved down in this direction, right? Because the mantle is enriched in the lighter isotopes. So as you lose the lighter isotopes, you enrich the heavier isotope, you would move down this direction. Okay, so these are some krypton isotope measurements. The atmospheric composition lies right there. This is the sun's composition. This is sort of average carbonaceous chondrite. That's what AVCC stands for. These are the well gas measurements, meaning that the mantle is somewhere up there. Okay.
Can you explain this? This is kind of bizarre, the well gas. If you want to give a couple of examples.
So the well gases are thought to sample. So the question is, what are these well gases? So you see them in sort of areas of spreading, such as the Rio Grande Rift. And we think that they are a mixture of air, crustal gases, and mantle-derived gases. And one reason why we think there's a very large fraction of mantle-derived gases in these samples is because helium isotope ratios are very close to what you see in mid-ocean ridge basalts. Neon isotope ratios are very close to what we see in mid-ocean ridge basalts. So there's a very high component of mantle-derived noble gases in these sort of continental well gases, which is kind of actually surprising. The point in this slide, though, is if this is the atmosphere and this is the mantle, now the mantle is enriched in the heavier isotope compared to the atmosphere. Okay? So if the mantle composition lies here, most probably actually the mantle composition lies there because you're seeing some kind of a atmospheric contamination in these well gases. But let's assume that the mantle is here. If you outgas this mantle composition and you start losing the atmosphere, you will move up in this direction, meaning you're trending away from the atmospheric composition. So whereas I told you that in xenon space, if you outgassed this mantle composition and you started losing it, you would move back to the air composition. In terms of the krypton space, if you outgassed this mantle composition and you start losing the atmosphere, you would trend further away from air. So this is what's shown. This is what is shown schematically here. So atmosphere, mantle. This is increasing 128, 130, increasing 82, 84. So basically, in this xenon space, it's the atmosphere that's enriched in the lighter isotope. In krypton space, it is the mantle that's enriched. Sorry, it's the mantle that is depleted in the lighter isotope. And mass fractionation moves you in this direction. So if you outgas again this mantle composition, you would move over there, and that's the measured atmospheric composition. So when you start combining all of these different systems, it is impossible to outgas mantle-derived volatiles and match the atmospheric noble gas patterns. So the combination of neon, krypton, and xenon basically rules that possibility out. Okay. So the option then is you have to bring in the atmospheric noble gases after the moon-forming giant impact. And this comes back to what Rick asked initially. Could you explain the two different xenon reservoirs through late addition of material after the moon-forming giant impact? And the answer would be maybe, but remember, if this is the composition of the late veneer, you haven't completely mixed in that late veneer component in the mantle, because the mantle and the atmosphere are still different in xenon isotope composition. So if you want to explain the difference between mid-ocean ridge source and the plume source through a late veneer, then you have to bring in that late veneer component after the moon-forming impact. And then on top of that, you have to bring in something else that is different to explain the atmospheric composition, meaning that you have two different flavors of a late veneer component. And that was my rationale for arguing that this is not a late veneer signal, but this is a signal of differences in the mantle degassing rates within the first 100 million years of Earth's history.
Can you say anything about the mass of the late veneer that would be required?
The short answer is no. I can't tell you about, in terms of explaining the noble gas budget, as to how much you would need. And the reason I can't tell you that is because I'm going to argue that if you want to explain the atmospheric noble gases through a late veneer, you still have to invoke a meteorite that we haven't put our hands on yet. Because, again, this comes back to the krypton composition of the Earth's atmosphere. Up here, the krypton composition of the Earth's atmosphere doesn't look like meteorites, it doesn't look like the sun. So you just cannot say that's my favorite meteorite for explaining the atmospheric composition.
What about if we get outgassing of a mantle reservoir that we don't have today anymore, either because it's not there anymore, or because it's too refractory to melt?
So the other option was, what if you outgassed a reservoir very early on in Earth's history that is not there anymore because it might have been destroyed or it's now too refractory to melt? I don't have an answer to that. How would you test it?
Yeah, would you test it? It's the same as the healing of meteorites we haven't seen.
Yeah.
Would you see this like?
No, I don't seem to like it. All I'm saying is that you can't yet put a finger on and say that's the meteorite that explains this composition.
So what percentage of the meteorites do you think?
I'm going to have Bill answer that question.
I guess I'm not clear on exactly what limit you're arguing for. Are you saying that the late veneer is all of the rare gases in the atmosphere, or that the rare gases in the atmosphere are a mixture of a significant amount of late veneer and mantle gas?
I'm arguing that probably greater than 90% of the rare gases in the atmosphere are from a late veneer, meaning that they're not from degassing the mantle. And you can sort of see that if you go back to the to this mixing plot. The mantle is up here. This is much, much closer to this meteoritic component than it's to the mantle composition. So at least 90%, or probably greater than 90%, is from a late veneer.
I'm not entirely sure, but I think that these long periodic comets are actually within the solar system. They might have like some overprint on the isotopic systems that are not from our solar.
Yes. So this comes back to what about... so the question was, what about some long period comets which might actually be coming in from the very outer edges of our solar system and the Oort cloud? People have invoked comets to explain rare gases in the atmosphere. The drawback is that we don't have a direct measurement of rare gases in comets. We have some measurements of what the elemental abundance could be based upon lab experiments involving amorphous ice at 20 Kelvin to 40 Kelvin temperatures, but we have no idea what their isotopic compositions are going to be. And we're also not clear whether you could take those lab experiments and extrapolate it for comets. So comets are obviously a possible reservoir, but unless we actually make these measurements, it's going to be hard to test it. So for example, we now have measurements of comets associated with the Stardust mission, but obviously you can't do any rare gas measurements on those, or it's very hard to do. I think the only rare gas measurement that was done was for helium and neon, and they looked similar to nebular gases, but obviously the more interesting ones are going to be krypton and xenon, and that's not going to be possible with 3 10-micron size grains.
This is similar to what Martin was saying, right, that the atmosphere looks chondritic in terms of rare gases. But he did point out one very important exception, or maybe more than one, which is nitrogen.
Yeah. So the atmospheric abundance, I would strongly argue, looks like chondritic meteorites. The isotopic ratios don't look like chondritic meteorites. And here is the example. If this is our sampling of all the different chondritic meteorites, and this is the atmosphere. It's very close, but it doesn't quite look like it. The abundance is the nitrogen is all.
And Martin's explanation for that is that the nitrogen is somewhere in the interior,
Yeah.
like a core, which requires that a lot of the delivery happens before the
Yeah. This is probably not going to be very clear to everybody, but he based his inventory on the helium to argon 40 ratio, and he assumed pretty high potassium concentrations. So his inventories could be higher than what might actually be in the mantle today, if the potassium content is lower, because ultimately he's tied to the production of argon 40.
Yeah, but his argument is if you just take the rare gases concentrations, any rare gas concentrations in the atmosphere, take chondritic, say, xenon, nitrogen, or something like that, then you end up with 10 moles of nitrogen in the atmosphere.
Yeah, instead of 1. Yeah. So I guess the take-home point that I wanted to make is that if you look at all of these rare gases, we don't think that you can explain the rare gases through outgassing mantle volatiles and then isotopically fractionating it. We think you require a late delivery after the moon-forming impact. It's possible that that could be chondritic meteorites. It's possible it could be comets, although we quite haven't sampled anything that looks exactly like what we see in the atmosphere. So moving over to some of the other volatiles, like water and carbon dioxide, if the argument is that most of these rare gases are coming in after the giant impact, then it means most of the carbon and most of the water should also be coming in after the giant impact. And it's very likely that during the end of accretion, heavy bombardment likely maintained a hot steam atmosphere. Mark Harrison showed you very nice evidence based on the zircons that there was liquid water probably as early as 4.3 to probably 4.4 billion years. Unfortunately, what I think the zircons do not tell you is whether you had stable oceans all the way from 4.3 to the present time. Because it's likely that if you had large impacts, you could have generated steam atmospheres. So this is, and I think Dave Stevenson mentioned this in his chalk talk, the impact frustration of life, which is that with every big impact, you end up generating steam atmospheres. And I'm just going to show you one example of this.
It's also feasible if we had a snowballer.
It is, and hopefully I'll get there, yeah. So here is an example of, this is the South Pole Aiken crater. It's about 2,500 kilometers in diameter. And this is a paper by Kevin Zalny and his colleague who looked at the consequence of an impactor of that size. So this is basically surface temperature up here following the impact. This is time. And basically you would generate a steam atmosphere. The surface ocean would get up to temperatures on the order of about 500. Associated with this impact, you would have a rock vapor plume that would basically distribute itself throughout the Earth. And then as that vapor cools, it'll condense. So both the radiation from the vapor heats the oceans as well as the condensing rain clouds from this vapor is going to end up hitting the oceans to something on the order of about 500 Kelvin or so. So that may be high enough to basically end up sterilizing anything that was present in the ocean. So that's what David referred to in terms of the impact frustration of life. So every time you had one of these impactors the size of South Pole Aiken, you would generate steam atmospheres, lead to some close to a boiling point, or actually slightly higher than the boiling point of water. But the steam atmosphere collapses pretty quickly. In roughly about 100 years, the steam atmosphere is gone. So the surface cools off very quickly. And these calculations are based on something like 1 bar nitrogen pressures.
I'm sorry, and this is a South Pole Aiken type impact on Earth?
That's right, yeah.
Okay. And Abramoff and Moises pointed out that this is at the high end, but in fact, you could actually increase the portion of the Earth that sustains life by creating hydrothermal subsurface.
That's right. That's right. So the point is that in terms of impacts actually hurt and they can help in terms of prebiotic chemistry, because they can help because, as I'll show you, it might lead to some interesting chemistry associated with impact degassing, and it might hurt because, as I just showed you, it would generate steam atmospheres with 500 degree Kelvin temperatures in the surface ocean. You could blow off some of the atmosphere associated with these impacts. But I wanted to touch primarily upon impact degassing, and this goes back to Harold Urey's work in the 1950s. So the idea originally was that if the Earth grew as a cold body, you would have a reducing atmosphere. That's what you would get if you looked at the meteorites. But if the Earth was hot, if you had a magma ocean, if that was sufficiently oxidizing, you would have a water or CO2-rich atmosphere. Now, if I'm saying that most of the volatiles are coming in after the giant impact, then impact degassing of those kind of material is going to be very important. And quite surprisingly, the effects of impact degassing wasn't studied in detail until maybe the last 5 or 6 years. There is one master's thesis, I think, that goes back to the late 1970s, 1979 or so on, that looked at impact degassing of ordinary chondrites or carbonaceous chondrite, but it has only taken off in the last few years. And so here's an example of the kind of an atmosphere you would produce by impact degassing of a ordinary chondrite. So this is based. So this is the temperature on this axis. This is the concentration of the gases. So if you reach temperatures on the order of, say, between 1,000 and 1,500, notice that the dominant species in the atmosphere is going to be things like methane, H2, CO, and so on. So it's not primarily dominated by CO2 or water unless you get to fairly high temperatures. So in this kind of scenario, if you're bringing in ordinary chondrites, and I know Bill really likes that based on osmium isotopes, but anyway, so if you're bringing in things like ordinary chondrites that are fairly reduced, the outgassed volatiles from the ordinary chondrites are going to be fairly reducing. If you look at the calculations associated with carbonaceous chondrites, or specifically CI chondrites, in this case you start actually producing more oxidized atmosphere. Things like water and CO2 are dominant. At the same time, you do see that H2, CO, H2S are actually fairly abundant.
Could you describe more about exactly what this calculation is and what the
Yes, so
size,
what the
relative size of the impactor of the body is?
So this is a calculation based on about 1 to 10 bars of atmospheric pressure. It's based on looking at chemical equilibrium between the species, and the way you solve for all of these species is through Gibbs free energy minimization. Other than that, I don't know too much in terms of the details of the calculations. I don't know if Mark has. I haven't.
It's big code that
yeah.
Gas components and has
That's right.
thermodynamics of
All the
supposedly all the relevant minerals.
Of all the relevant minerals.
There are sometimes issues with these because it depends on what your starting composition is, and when you for example, an ordinary chondrite, it's pretty clear what a carbonaceous chondrite. There's an awful lot of fairly reduced carbonaceous material in that.
That's right.
And depending on
In the ordinary or in the carbonaceous? In the carbonaceous chondrite. But that's why in the carbonaceous chondrite, you end up dominated by H2O and CO2.
Well, I'm not so convinced of that, right? For the ordinary chondrite, it's clear you're going to metal or so forth.
Yeah.
For the carbonaceous chondrite, there's no metal, so it looks kind of oxidized. But there's a lot of organic matter.
There's a lot of organic matter, yeah. But the point here is that even if you believe this is right, there is still substantial amounts of H2 and CO compared to what you would think you would get if you outgassed a magma ocean.
Sorry, these are the temperatures in the atmosphere after the impact.
Yeah.
Not during the impact. I mean, the impactor is going to go through outrageous temperatures. So
Yeah.
This is close to the atmosphere.
Yeah. That's right. That's right. Yeah. So the point is that it is quite possible that the atmosphere was reducing or mildly reducing, and I think that concept was basically non-existent even 10 years ago. But I think it's now pretty much back in play. It is conceivable that at least for short amounts of time after one of these impacts, that the atmosphere could have been reducing. So if we dial the clock a little bit further, this comes back to when do we think a stable ocean might have come into play. And we think that that might have happened probably by 3.6, 3.8 probably. So these are examples of metamorphosed pillow basalts at Ishua. So these are the pillows, and we know based on the present day world, pillow basalts erupted underwater. These are banded iron formations where we think we see these sedimentary layerings. These go back to 3.6 to 3.8. These are also metasediments up in Aquila, which we think date back to 3.8 billion years. And we think all of these sedimentary rocks require there to be an ocean. So in the geological record, I think it is fairly convincing if you want to argue that stable oceans existed by 3.8 billion years. Now, one of the surprising things is the rock record really takes off at about 3.5. And the first real evidence that you have of global glaciation doesn't happen until about 2.5, 2.4 billion years. So at least in the rock record, for the first 2 billion years, the planet could have been completely frozen, but the rock record hasn't recorded it. And as a matter of fact, at least from 3.5 to 2.5, the rock record says that there wasn't global glaciation. And why am I bringing that up? And the reason is, if you look at the sun, 4.5 billion years ago, the sun was about 30% dimmer. So here is the solar luminosity relative to today. So today's up there. So back at about 4.5 billion years, the solar luminosity was about 0.7. And this curve shows you the amount of CO2, or a greenhouse gas, that's required to be present in the atmosphere to keep the planet above freezing. So for a luminosity at 0.7, you would need something that is larger than 1/10 of a bar of CO2. The present-day atmosphere is about there. So something like more than 3 orders of magnitude higher CO2 contents. If you want to be up at about 280, then it's obviously much higher.
What if it's methane?
I'll come to that again in a second. So CO2 as a greenhouse is a potential option. The drawback is this is still quite controversial. If you look at measurements of soils, if you have a very high CO2 content as implied by these amounts of CO2, you should start getting iron carbonates or siderites in soils. And there isn't very good evidence that you actually see siderite in the soil. So these are examples of where the soil measurements constrain the Archean partial pressure of CO2 to be. So people have invoked on methane as an additional greenhouse gas, and obviously methane is a much more potent greenhouse gas. You can't have a pure methane atmosphere because by the time the methane to CO2 ratio goes above 1, you start forming methane haze, and methane haze is very, very efficient in terms of scattering solar radiation back out. So as soon as you form methane haze, you start cooling the planet. And you start forming methane haze again when the methane to CO2 ratio exceeds 1. So you could have a little bit of a methane, but not too high a concentration. So as far as I know, this is still an open question as to what the greenhouse gas in the Archean was that kept the planet above freezing. It's probably some combination of methane, some combination of CO2, something to do with the cloud structure in the Archean, which is obviously a very difficult thing to address because clouds aren't properly handled even in GCMs that are looking at present-day climate systems. So, like Mantle geochemists have argued for a long time about the structure of the Earth, this faint young sun paradox was pointed out probably in the 60s by Ringwood, not Ted Ringwood, some other Ringwood, and then subsequently popularized by Sagan.
Sujoy, you made some comment about siderite. There is a rock record that's good enough to say that there isn't siderite in soil.
Yeah.
2.5 billion years ago, it's a long time ago. It looks pretty good.
2.5 billion years ago, so the rock record is fairly good since 3 on, and between 2.5 and 3, again, I think the argument is you don't see siderites in sort of these paleosol layers. So the last slide that I'll talk about is the mass-independent fractionation of sulfur isotopes. So basically, prior to the rise of oxygen, UV photolysis of SO2 would produce mass-independent fractionation in sulfur, which would be transmitted into the oceans and then into the sediments. And so the sediments would be recording this cap delta 33 signal at values either above or below 0. So when you look at the rock record, all the way back from the start of the rock record, you see this mass-independent fractionation in the sulfur isotopes. Seems to become slightly smaller in magnitude at about between 3 and 3.4, and then prior to the rise of oxygen, which happens there, this just takes off. And it's believed that this is not some sort of a preservation effect, that this is a real signal, that the actual magnitude of the mass-independent sulfur isotopes were smaller in the earliest Archean, and then became even smaller, and then jumped up right before the great oxidation event. And again, it's not quite clear what is driving that. Itai Halavi and colleagues basically suggested one possible way of doing this is by controlling the SO2 to H2S ratio of mantle gases. And it's not necessarily that you have to change the oxidation state of the mantle, but one way of changing this ratio is by erupting subaerially versus erupting in submarine conditions. And the idea is that if at this point, so this is their SO2 to H2S ratio, this was low. And then the lower the SO2 to H2S ratio, the more diminished the mass-independent fractionation. And then as this ratio jumps up in the just prior to the rise of oxygen, you see this massive increase in the mass-independent sulfur isotope fractionations. Wow, I have a permanent marker. And so the argument is that this is being modulated by interaction of the surface reservoirs with the mantle, either through this change of SO2 to H2S directly from the outgassed volatiles, or because you're erupting in submarine versus subaerial conditions. And I think that's all I had. Quentin.
Yeah,
Yeah, I'm always struck in the discussion of inputs of gases to the earlier. We always wind up with the discussion of comets versus carbonaceous chondrites and solar nebula and what could it be. There's one population of objects, or a continuum of population of objects we see nothing of, which is, let's say, Sirius size, sort of circa 1,000 kilometers each. So my question is how much thought has been given to the parent nuclei within the early forming bodies being possibly preferentially stripped off? For example, 244 plutonium probably goes into a protocrust. That would be my guess.
Mm-hmm.
For objects that have extremely complex impact histories, could you simply get a variable amount of 244 plutonium from the impact history on Sirius-type bodies, in which dozens and dozens go into the protoplanet, that could in turn modulate your isotope ratios or your noble gas ratios? And how much thought has been given to the objects going in and the parent nuclei of these things in their history?
So I think there are two aspects to this. You're absolutely right in terms of maybe stripping off, say, crusts of planetesimals, which would have things like plutonium-244, and that could lead to different amounts of plutonium-244 that's coming in. People are actually now starting to look at collisional erosions in terms of also looking at this issue of samarium-neodymium fractionation. And obviously, if you have time-varying plutonium delivery, it will affect things like the radiogenic xenon isotopes. But that's not going to be important in looking at the primordial isotopes, which are not affected by the production of, say, xenon-136, because those are primordial isotopes. So there's no production of these isotopes in the solar system.
But the question that I would pose then is that within 1,000-kilometer size body, say 1,500-kilometer size body, are you so certain that we know the loss mechanisms associated with loss of, let's say, primordial?
No, I know exactly where you're going, and the answer is I don't think we know that very well. So this goes back to this whole issue that the pattern that you see looks very similar to carbonaceous chondrites, but the isotope ratios don't, and that's telling us something fundamental, like we don't really understand how you're generating these isotope ratios. We don't know why the carbonaceous chondrites are so different in their isotope composition compared to the sun. We don't know why carbonaceous chondrites have this 7 different neon components in them. You can pick out any single meteorite and they'll have it. It's incredible. So we don't really understand those processes yet.
Thanks.
Is there a way to fractionate krypton from xenon, for example, in a scenario?
Again, if you have bulk ejection of the atmosphere, you won't be fractionating one element from the other. If you have some sort of a process that induces isotopic fractionation, it will very well also lead to elemental fractionations. But the point is that the fractionation goes in 2 different directions, and that's why it's such a difficult observation to explain. Now, one can always come in and say those well gas data are bad, but I don't see any reason why we should make that claim.
So Sujoy, this issue of collisional erosion, what's often skipped over when people are talking about it, if you want to use it to explain neodymium, for example, and you're thinking about eroding the kind of crust we know on planetesimals, like eucrite, for example, the level of incompatible element enrichment of those suggests that you have to remove a mass more or less equal to the whole mass of the lower mantle to explain the non-chondritic versus S/D ratio, for example. So
I completely agree.
It's a nice model, but you have to remove a lot.
You have to remove a lot. I agree. But these simulations, the impact simulations, I think are just taking off. So we'll have to wait at least a year and see that if it's feasible. I agree that I have doubts that you can lose that amount of mass, but who knows? Lunchtime?